Hi, my name is Nicholas Corsello, and I'm going to be talking today about the kinetics of the saponification of ethyl acetate. So what does that mean? It is this equation right here. So we're going to take our ethyl acetate and we're going to react it with our hydroxide ion, or in this case, NaOH, and we're going to get our acetate ion back out and ethanol. And it's okay, I can do this reaction 21. So why do we care about this at all? Well, just like any other reaction, we want to know the mechanism. We want to know what makes it go, right? So we have a proposed mechanism here. As you can see, we have our hydroxide. It's going to attack our ethyl acetate here, which is going to pop up our electrons, making this big structure, which is then going to collapse into our acetate and our ethanol ion, which is then just going to go into a proton transfer and going to get our products. So I ask again, why do we care? Well, when we have mechanisms like this, it's nice to have our sticks and our arrows and kind of just trust that, but we also want to have data and we want to be able to verify that this makes sense, right? And so we're going to do that today via kinetics. We're going to make sure that the kinetic data that we get makes sense and backs up this mechanism right here. And we'll talk about how once we get that data. So how are we going to get kinetic data? We're going to do that through conductivity. So kinetics just talks about how fast the concentration of our solution changes, or our concentration of our reactants decays. And it's a little bit hard to measure concentration just staring at a bunch of clear solutions that you toss into a beaker and are reacting. So what we're going to do is we're going to put our voltage into our solution, and then we are going to measure the conductivity. So if we look at our nice little equation that popped up down here, we have a kappa naught, which is going to be our conductivity at time equals 0, or before any reaction has happened, ideally. Then we're going to have our kappa, which is our conductivity at any point throughout the reaction. That's going to be what's varying. Then we're going to have our kappa naught again, and our kappa infinity, which is going to be our conductivity after the whole reaction has occurred. And we just measured that by letting the solution sit for a while, doing other things, going on our phone, and then measuring it a little bit later, and once we think everything has reacted, and we are assuming that our reaction goes pretty much to completion. So once you take this ratio, you will have a whole bunch of kappa values. We measured our conductivity at every 10-second interval, and you can turn each one of those using these three constants into a ratio here. And this ratio is just another marker of how much the reaction has progressed. So that's going to be our substitute for concentration, essentially. So at each point of conductivity that you put in, you're just seeing how far it is from the beginning and the end. So in order to do this, we're going to do 4 different runs. The first 2 are going to be at 0.2 molar ethyl acetate, and the reason that's going to be at that is because our sodium hydroxide concentration is 0.02. So we know that for kinetics, if it depends on both, if the rate depends on both the ethyl acetate and the sodium hydroxide, it can be a little bit hard to measure the reaction rate of that. So what we're going to do is we're going to have the ethyl acetate in a lot of excess, so that if it depends on the ethyl acetate, it will be at such a high excess that's really only depending on the hydroxide for those runs. And that way we can see the order of the hydroxide, and that'll help us determine the order of the ethyl acetate. And then we have 2 more runs to do exactly what I just said, where there are more or less equal amounts. There's a slight excess of ethyl acetate, but we can determine both of them now, since we will have 2 runs where it's just depending on one of them. We have a difference between room temperature and high temperature because temperature can impact kinetics a lot, so we want to see that difference. We want to make sure that for the different temperatures, there is no change in order, because that shouldn't depend on temperature, but there should be a change in rate and rate constant, because those things depend on temperature. Well, rate depends on rate constant, which depends on temperature. All right, great. So we did our 4 runs, we did our conductivity, and we're going to turn our ratios first. We're going to plot them with our first order graphs. So as you see here, we have our ratio that I talked about earlier, and we're going to plot those in a first order relationship with time and see, and if it turns out to be linear or fits a linear plot well, then that is what we will conclude that the relationship is. So let's start here with our 0.2 molar. You can see that for both of these guys, they fit a linear plot well. And so it's fair to assume that since these are our ones where we have one of the reactants in excess called the isolation method, that the one that is not in excess is going to be first order because it fits this really well. and that would be our hydroxide. So we're going to keep that in our back pocket. And we go down here and we see that for this ethyl acetate at high temperature, we actually are fitting a linear line pretty well. But since we're over here at room temperature and this doesn't fit that well, and it should be the same, we're going to say that it's probably not first order overall when considering both reactants, just when we're considering the sodium hydroxide. So since we want to know what it is in terms of both, we're going to keep moving on and we're going to plot it in terms of the second order. Again, here's our ratio, and we are plotting it in a second order relationship to temperature. I plotted both of our 0.2 molar runs again, just to show that it doesn't fit these guys quite as well as it fits the first order. So we're pretty safe in our conclusion that's first order with respect to sodium hydroxide, or hydroxide ion specifically. Now we go down here and we see that we still aren't finding a great fit for our ethyl acetate. I'm sorry, for our 0.05 molar ethyl acetate. So we're trying to find the order of the ethyl acetate reactant. Which it calls for a distinction. When I say second order here, this is the relationship if the reaction was second order with respect to one reactant. So if it was second order with respect to ethyl acetate and zero order with respect to sodium hydroxide, which we know isn't the case, just for example, or vice versa. So we're seeing that this isn't the case. So what we're going to do is we're going to take the other scenario that can make a second order before moving on to crazy things like third order. And we're going to see what would happen if we made it second order in the sense that it is first order with respect to ethyl acetate and first order with respect to sodium hydroxide, making it second order overall. And we see that if we do that with this big ugly relationship right here, you get actually some nice linear plots. And so we can pretty safely conclude that our reaction is first order with respect to ethyl acetate and with respect to sodium hydroxide, making it second order overall. So this part is what I just said. It is our 4 runs and our order that we concluded for each. Now we have our rate constant. So for our first order equations, our rate constant is the opposite or the negative of the slope of that line. So we have our 2 beautiful rate constants right here. Notice that they are different at temperature, which is something that we want to see because the rate constant does depend on temperature. So when we're increasing temperature from room temp to high temperature, which is about 50 degrees Celsius, we are seeing a pretty a change in rate constant, which is great. Now we go down here to room temperature and we are seeing, I'm sorry, for 0.05 molar, and we're seeing different rate constants because it's a different rate law entirely. And because of that, we're seeing different units because this is second order overall, while this is first order. It's pseudo first order, I suppose you could say. Now, I want to know what the activation energy is because that'll tell me a lot about the mechanism. And so I'm going to use this equation right here. This is probably what people are a little bit more used to in terms of activation energy, but I don't have that fancy A yet. So we're going to start here and we're going to take our 2 different rate constants at 2 different temperatures. And we're going to do this twice, both for our 2 different concentrations. And we're going to get 2 different activation energies. Lower for the 0.2 molar, which again should make sense. We have excess, so it takes less energy for the reaction to go, since it's just more likely to happen. Now we're going to take this part and we're going to solve for our A, and we're going to get our 3 exponentials, which agree pretty nicely with each other. So moving on to discussion, this was really nice because we can get a nice understanding of kinetics. You can see how the different variables interrupt each other. And so that in its own learning process is worthwhile, but we, again, care about this mechanism. So we want to make sure it makes sense, and it does, right? If we look at our first step here, we have our hydroxide ion colliding with this ethyl acetate. And so if it's just a collision between these 2 that we're worrying about, we are going to look at, it's going to depend on the concentrations of those equally, in which case we will have a first order with respect to each of them reaction, second order overall, as I said. So it makes sense with our mechanism. We have data to back it up. One interesting question to ask would be, what would happen if we change this from a ethyl acetate to a methyl acetate, or even to, let's say, like a propyl acetate? And that could influence a couple of things. It could increase the sterics around here. It could increase the energetics of this collapse. So maybe it's more or less likely for this to collapse and move the electrons over here if there's more or less alkyl groups at the end. And so if it makes this, if it slows this step down, it's possible that it is, this is no longer the only thing we have to consider, the collision between these 2, and it makes the rate law more complicated. One last thing that we should discuss is that if we take our activation energy and we plug this into this formula to get our enthalpy of our transition state, we get this value. And then if we take our enthalpy and we turn it into entropy, the transition state, we get this value. So this makes sense. First of all, got to put energy in to get the transition state. That's kind of the concept of activation energy as well. But in terms of entropy, we see that we are increasing in entropy, which might not make sense at first because we're taking two things and combining them into one thing. But from the entropy loss that we're taking with this hydroxide, we are creating a really complex molecule and we're freeing up free rotation around here. We're losing the double bond. And so making a complex thing that's kind of spinning around. So it does make sense that we are gaining entropy. And that is a really good way to look at it and discuss how we can look at kinetic data and take it to something more theoretical like a mechanism. Thank you. That's all I got.